Okay, great. Terrific to have everyone here. We're going to be continuing today our discussion of some basic elements of agent-based models, and in fact, continuing our emphasis on characterizations of state. And we'll next time be extending that to state updates more generally. But today, I really wanted to speak about in further depth about some of the differences that present themselves between compartmental and individual-based models, including agent-based models. I further wanted to be able to go into some of the salient advantages there, and where possible, illustrate them by specific examples. This lecture will involve some overlap in discussion with our last one. However, it is going to do so with a somewhat different emphasis in a somewhat different theme or sort of cross-cutting motive, which will be to highlight many of the salient differences between ABMs and aggregate compartmental models, particularly aggregate models, and to show some of those as that reflect advantages. We will be using any logic at one point within today's lecture, so if you have that up and could have that ready, that will speed up some of the coverage. Okay, so with that intro, I'm going to jump in to some slides and then an interactive component here. Okay, here we go. So those who joined us last time will recall that we spoke about characteristics of agent-based models. We reminded ourselves that agent-based models, as some of their many key properties, have a characterization of state and rules for evolving state. And generally, at a high level, those characteristics, having state and rules for evolving state, are true of any dynamic modeling framework. And that's what makes it a dynamic framework. But I noted some salient features quite specific to individual-based models and prominent within agent-based models as examples of that, that we can represent state of different sorts: discrete, continuous, relational, positional. And I argued that this flexibility was important in many examples. We'll be seeing rather detailed discussion of some of the advantages of characterizing these matters relationally or positionally. Maybe someone could get the door, maybe something left in here. Oh yeah, the toque is over there somewhere. Presumably. Great, there you go.
Sorry about that.
No worries at all. No worries. Good you came by. You need the toque today. Yeah, thanks. Okay, so agent-based state can be seen in agent-based models in a variety of these characteristics. Certain characteristics play a more central role in some models than others. Networks, spatial location as mediators to interaction or access to resources, etc. But ABMs have a particularly notable set of advantages that extend from their representation of state. And I'm going to highlight these here because they were kind of in the background in our last discussion. I alluded to them, but I didn't really underscore them. And I didn't think in some cases that I did an adequate job of illustrating. So I'd like to go through them with you. We're going to be recurrently coming back to this slide. I'd like to go through successive ones of these and illustrate what I mean by each of them. Okay. So to that end, I'm going to remind us of our coverage of state charts last time. I'm not going to remind you of some of their basics again, but just to situate us with the recognition of state charts. And I want to note the first of these properties, the capacity to characterize memory-full transitions compared to memory-less transitions, which is what we see in compartmental modeling and aggregate modeling. Here we have the capacity within a state chart, within one of these transitions, and as evidenced by the different icons you see here, to make use of different types of rules mediating the timing, or indeed the occurrence of an agent down that transition. And what I'm going to be highlighting, what I'm highlighting here in this particular point, is that process of proceeding can, in general, will depend on how long an agent has been in the, how quickly they leave down a given transition depends how long they have been in the state once that transition comes. So in this case, this transition here, it's a timeout transition, and the chance per unit time that they leave from this state down that transition depends. Indeed, it depends entirely how long they've spent here. But in general, we can have transition types that are extraordinarily flexible for this. They can depend on a fixed rate, in which case they're memoryless, an invariant rate that's the same per unit time. That would mean every day or something, someone has the same kick at the can of leaving this transition. It's a continuous notion. It's a hazard rate. They have the same chance per unit time, not the same probability, but the same chance per unit time of leaving. And that would be memoryless. But the other transitions shown in general will be memory full. These transitions of a timeout, if we have a variable rate, if we depended on a message being received, if there's some predicate, some condition that allows us to proceed, or if we're waiting until we arrive at a location. In general, we will move beyond the memoryless assumptions we traditionally see with stock and flow or with compartmental models moving between states. Okay, a second point that I want to make is that, and again, it was in the background, I alluded to it a number of times, but it perhaps wasn't brought out as saliently as an advantage here. We can simultaneously track the progress of an individual along multiple dimensions. So I'd shown last time, by way of sort of explaining state charts, that we can have multiple state charts and their algebras, multiple state charts next to each other, like shown here. These represent different concerns. And what I emphasized last time was that when we have multiple state charts next to each other, either here or like this or like this or here or here, for each and every one of those state charts, an agent will be in a specific simple state. By simple state, I mean sort of the innermost state at any one time, right? So it's not that a person is in only this state and the rest they're not in. No. They're in some state for this first one, some state for the second one, some state for this third one, some state for this fourth one, some state, etc. Now, sometimes that state that they're in is itself within nested states, and they can be said to be in those nested states. But I'm talking about the simplest, the so-called simple state, innermost state here. They're in exactly one. Now, this is important because these state charts, putting them side by side, allow us to simultaneously track an evolution of an individual along those multiple dimensions. That is convenient. We can characterize as a matter of separation of concerns, characterize concerns related to the correction system here, to the healthcare system here, to their status with respect to using opioids here, and for their willingness, their attitudes with respect to or readiness for behavior change here, etc., and have a nice parceling out of our concerns into different specific representations. That supports some model transparency. Each type of concern goes in its own place, as it were. It's appropriately separated from the others, encapsulated within a given state chart. That's an advantage of having those state charts delineated separately. When we compare that to what we see within a compartmental model, the difference starts to become more stark. We noted last time that, at a very high level, by appearances, if you think of them as kind of graphs with some, specific types of bells and whistles, you might think that the structural similarity here between a stock and flow model, shown here, a compartmental model where we count the number of people here, versus an agent-based model where each person is in a specific state, you might be excused for thinking that they're potato, potato, tomato, tomato, that they're just different sides of the same coin. In terms of their characterization, in terms of their properties, while there is definitely some relationship here, the underlying mathematics and the underlying scaling, the underlying characteristics of this representation and its implication as we add more elements of heterogeneity are very different. And I started to emphasize this in my final remarks last time, but I want to do it more justice today because I was just sort of gesturing at it last time. So at a certain level, you might think that these are different equivalent representations, but it's understandable, but it's mistaken. You can legitimately regard this one as a abstraction of this one, as a summarizing up across a population. But the actual implications for what diagrams mean and how they combine are rather different. And I want to reflect on this, particularly for those who are from aggregate modeling background. With aggregate modeling background, with aggregate models, compartmental models, stock and flow models, we characterize a population, we organize our model, as it were, parcel it out into pieces that reflect the states and characteristics of people in that population. If we're going to distinguish people, because each of these stocks, each of these state variables represents some count of people with the same characteristics. If we're to distinguish sets of parties, or sets of people, we do so by putting them in different bins, right? It's by putting them in one of these bins, counting them as part of a different set of people that we distinguish them. We characterize separately their state and characteristics. So it follows that in an aggregate model, we organize the model. It's subdivided up according to state and characteristic. And each compartment here, each stock, each state variable counts the number of people there, right? I will note that if we had multiple cities, for example, and we wish to characterize susceptible, infected, recovered, exposed in different cities, we could put that down and they'd be kind of next to each other, those for one city, those for another city. If we wanted to then characterize it for the whole region, we could have variables that would sum up the susceptibles for city A with the susceptibles for city B with the susceptibles for city C and get a total count. Same thing with exposed, infected, recovered. Those variables would all be kind of at the same level of the diagram. There's no nesting in this diagram. There's no hierarchy. There's no higher level, lower level sort of structure captured here. All variables are kind of at the same level of the diagram. By contrast, in agent-based modeling, we have a very different organization. In a way, it's turning this on its head. Well, in aggregate models, we subdivided the model. We organized model by state and characteristics, putting people in different bins based on their characteristics. With an agent-based model, the organization, the fundamental unit of organization, is not the group of people according to characteristics and state. No. It's individuals, right? Those are the fundamental units within the model. And each unit maintains its own state and characteristics, its attributes. Instead of binning people up into ones, each person carries its own. And we can capture nested relationships, people within families, within neighborhoods, within cities, within region, within province, in a way that's nested in the model, in fact. And we'll see models like this. We can mirror that nesting structure, mimic it within the model, and have kind of a similar nesting within the model. We can capture families, and the families have people within them. They reference people that are in them. We can have neighborhoods that reference the families who live in that neighborhood or what have you. And similarly, networked relations in the model can be characterized as networks of agents that mimic those in the world instead of being characterized, say, as mixing matrices, characterizing the mixing of people in one city with those in another city, or one age group of those in another age group. So here, rather than stocks counting the number of individuals who have certain characteristics, a certain state and certain properties, certain attributes, instead we have individuals who carry their own attributes and evolve those attributes over time, and we can summarize upwards from there. I will note that here, with respect to these characteristics, if we have a state chart here, we have stock and flows here. In both cases, we're characterizing things as having a discrete breakdown of people's state. Unlike aggregate stock and flows, within a state chart, for a given person, they're in a specific state of that state chart at a given time, right? And here, it's not like there's a count of people in this. A given person is in a specific state. And we can keep track of how long that individual has been in that state and adjust their chance of leaving per unit time accordingly. By contrast, we cannot do that here. We can't keep track for each individual of how long they've been in the infective state and have their chance of leaving per unit time vary in that way. More fundamentally, in a way that has key implications for model transparency and nimbleness of model evolution, is the issue of the cursive dimensionality and representation. And again, I gestured at this in our closing minutes last time, but I want to do it. I want to do it a little bit more justice this time. So here, within a stock and flow model, within one of these, we could represent more than one sort of pathogen, more than one sort of process. We could have a set of compartments, a set of stocks here for COVID, labeled C, a set of stocks for flu, labeled F. We would have for each of these states, each of these compartments, each of these stocks, a count. All right. The count of people in this state people in the entire population who are susceptible to flu. You'll note okay. We may have lost a little bit there, but I'll continue. So you'll notice in my characterization of this, I noted that this stock, I sub C, characterizes the number of people in the population who are currently infected with COVID. This is for an aggregate model. This is for one of these guys, right? This stock S sub F is characterizing the count of people in the whole population who are currently susceptible for flu. What is not being captured in this diagram is the number who are number of people are simultaneously in this state and this one. What is being captured is a cross-sectional depiction in each case of the count who are in this state or the counter of that state, and there's no statement being made, no characterization being laid down by the model as to how many are in this combination of states if you put them side by side, right? It's just we're not capturing that. We're capturing two cross-sectional views of the population with respect to COVID, with respect to flu. Now, it may be due to concerns about co-infection, due to impacts of flu vaccination on risk of developing COVID, due to impacts of a recent infection at one on risk behavior, due to the fact that a person engaged in protective behaviors like mask wearing may protect themselves simultaneously from both of these. There may be a group who are wearing masks and therefore are less likely to get infected for COVID and less likely to get infected for flu. It may be that we really want to secure insight for policy or research reasons from characterizing that interaction, that simultaneously considering whether a given person, what state they're in with respect to the natural history of COVID infection, the natural history of flu infection. And maybe that we have some salient reasons to do so. And the means of doing so is straightforward but brutal from a standpoint of model transparency, from a standpoint of model nimbleness for evolution. We need to take here the product of all possibilities. So again, I noted last time in my gesturing at this that we have progression of COVID along here, along each of these rows. We are characterizing the natural history of COVID. Each of the columns, we are characterizing successive states of the flu. And a person could, for example, get infected by COVID, and before they develop infectivity, before they're infectious, they might get co-infected by flu and proceed down here, and then develop transmittivity for infection, for COVID, and then successively for flu, etc. Here, we're characterizing at once in a single aggregate model with a count of people in each of these locations. We're characterizing the set of individuals who are in particular with a particular state with respect to COVID, a particular state with respect to flu. And this general strategy works in its own brutal way for other characteristics, right? Here we're looking at successive stages of diabetes vertically in the columns, and successive stages here in terms of coronary artery disease and cardiovascular conditions. Where I think people will recognize where this starts to become burdensome to the point of being ruled out is if you want to capture progression and other characteristics, such as age, which would be yet another dimension coming out of the page. Or we wish to characterize some other comorbid situation, or whether someone's diagnosed or not with respect to diabetes. Maybe if so, they proceed more slowly down the stages of successive the natural history of diabetes, or whether they're diagnosed with respect to coronary cardiovascular disease. The point is that this sort of need to characterize two or more conditions within a stock and flow model is, again, multiplicative in its impact on model size, not additive. But what's perhaps more is more of a deeper issue beyond the memory footprint and the running time, which are affected in a big way. But often those are less bottlenecks for aggregate models because they're already pretty quick. The bigger issue here is often model transparency, the risk that by sheer copying and pasting or brutal sort of elaboration of this in a tedious sort of manner, you may make a mistake and overlook it. You may fail to catch that you've copied things directly rather than modifying them after copying them. You may discover that this level of elaboration starts to get in your way of the appreciation of the actual dynamics, particularly if you add a third dimension or a fourth dimension, really understanding what's going on where here and what the patterns of progression are gets quite challenging. Understanding the dynamics, understanding as well elements of the structure in a transparent way. Welcoming a stakeholder to critique this becomes more difficult. And what I'm highlighting, I hope you folks will recognize, harks back to our discussion of static heterogeneity, where we noted that adding a heterogeneity dimension, such as representing stages of retinopathy to this progression, or adding RSV to something like this, respiratory syncytial virus, another pathogen here with common risk factors. Adding that as another dimension leads to multiplicative sort of addition to the size of this model and number of details to keep track of within an aggregate model. By contrast, within an individual-based model, it is additive. We add another state chart here to those we keep track of, here. We add another state chart. We don't need to consider all combinations of states with those that are already there, which is really what's in store for us with aggregate models. Okay. So here, when we add heterogeneity with state charts, but more deeply with an individual-based characterization, when we add an element of state, be it characterized in a state chart, in a variable, in a characterization that uses a continuous dynamics representation, it's additive in terms of its impact on model size, not multiplicative. Okay, now for the next component, I'd like to actually call up an example model. I wanted to keep things a little bit interactive for at least part of this. So I put onto each of the course LMS sites a model that involves gestational diabetes. On the Fields LMS, I think its actual title begins with that. By contrast, here on University of Saskatchewan, it's called Introductory Teaching GDM v4. You don't see it? Sorry? Not in the modules? Okay, so here it is. It's called Gestational Diabetes for Fields. Let me just go and see. It's called Introductory here. Okay. It's under models used in class. Okay. Okay. So we're going to open this model up. Now, this model has many components to it. And I actually uploaded it alongside another model that's even more centrally about longitudinal data. This one accumulates longitudinal data, but it wasn't as defining a feature of the plan for it. But I want to highlight it. The other one, which I uploaded on longitudinal aspects of smoking history, centrally defines it, but it needs some libraries that I didn't have an easy way of sharing right there. And so I will upload those later, but those are to compute longitudinal statistics on individual characteristics. What I want to do here is I want to highlight within the model the fact that we have persons characterized, and each of these persons has characteristics characterized by state charts here, as well as by parameters, characterizing assumptions about characteristics that are static. And then, as we'll see, some hybrid components involving physical activity level, etc. Now, what's notable here in terms of characteristics is that there are some elements of state shown here as V for variable, which characterize current situation. For example, the color we use to distinguish someone or what have you. But also the count of gestational diabetes episodes that a given person has undergone. Or the weight category that they had on a pre-pregnancy basis before the current pregnancy. I want to highlight these because these are aspects of history. Count GDM episodes records how many bouts of gestational diabetes the individual depicted as an agent has encountered thus far. It's an aspect of their history that might be of interest to us for several reasons. One is it could be used to drive dynamics if we thought it was important, could play a causative role. Second of all, it could serve as an important outcome. for us to compare against empirical data. Thirdly, we might wish to use it to understand model dynamics that we see, to understand, for example, those at highest risk and what characteristics of their history might be most allow us to understand why they're at high risk. We might also use it for calibration to align our model, tune our parameter assumptions to align our model with empirical data. The pre-pregnancy weight category, we might be interested also in understanding for those who, before their pregnancy, were of a certain weight status, understanding outcomes based on that pre-pregnancy weight. So I wanted to highlight that, but I also wanted to highlight some additional aspects of transitions, and specifically for this transition to type 2 diabetes. I'm going to, I double-clicked on this to get a full focus on that. I double-clicked on it again to zoom out or to focus more broadly on the model. And I want to go look at the properties for this particular transition, what the rate is associated with this transition. And what I want to communicate here is that it does depend on aspects of their age, for example, which is changing. So here we have aspects of a person's current situation, their state, which are evolving, and aspects of their transitions, which depend on that. Although we don't have that directly shown here, we could easily have added the cumulatively spent in an obese state, for example, as a factor that we would take into account in their chance per year, per month, for example, or chance per year of developing type 2 diabetes from a pre-diabetic status. So here, we can take into account aspects of history of an individual. And if you go and you look at a person and you look at the functions available for the person, you will find that there are some aspects of their history which are accumulated and can be used to characterize their evolution, or as summary measures characterizing the population for outcomes or for calibration. The number of years they've spent in a diabetes state, in a diabetic state, for example. The number of years they spent obese, their cumulative obesity exposure, as it were, or the years they spent in an overweight but not obese state, or the years they spent in a pre-diabetic state. These are aspects of their history. And when it comes to understanding why certain agents in this ABM turn out certain ways, or understanding where the burden of type 2 diabetes is falling most centrally, or to understand who are the folks helped by certain interventions, in order to compare these model results again against empirical data or calibrate it to that data. These sort of historic measures, which are relatively straightforward to accumulate within an agent-based model. Indeed, you'll find them in many of the models in this model library, are really valuable pieces of information to keep around. And within an ABM, and I think I'll move back to the slides here, within an ABM, we have this ability to accumulate that sort of information. Within the other ABM, the longitudinal ABM on smoking, which again is available, but not at the moment, I didn't upload the extra libraries for statistics longitudinally, and so it's not runnable. But there too, you could have like the number of years smoked, as a factor which contributes to chance per year of developing heart disease. It's an aspect of their history. Or we could have their likelihood of falling back into being a current smoker, to relapsing into smoking, depend on their time since they quit smoking, with a recognition that often the chance per week that they fall back into smoking is vastly higher during their first month after having quitting than it is 10 years after quitting. If they can stay quit for 10 years, the chance of falling back into smoking on a per year basis is very small. By contrast, if they're still in their first month after quitting smoking, their chance per week of falling back into smoking is quite high. It's actually grimly high for those. Smoking is high. It has quite a strong physical dependence component. Psychological dependency associated that can be associated with it. So by characterizing history information, elements of an agent's history, and summarizing them like the number of pack years someone has smoked, the number of years someone smoked, and the time since they last quit, we can often get really useful variables for summarizing model state and for shaping model evolution. So those components speak to this accumulation of history information as a salient feature. The final thing that I just want to highlight is it has the same features we talked about in broad terms, the same features for static heterogeneity. Here, if we want to represent new dimensions of state, I emphasized it before, we need to multiply the size of a stock and flow model. We need to add in compartments in a way that with a cone of those compartments that rises geometrically with, or you could say exponentially if you want to consider it as a continuous variable, with the number of dimensions of heterogeneity. So if we have just one dimension of heterogeneity, just this, we might have 4. If we have 2 dimensions, we'll have 4 times 4 here because we have 4 in each. If we had 3 with another dimension of size 4, we'd have 4 to the 3rd power, 4 cubed. If we have yet a 4th one, it would be 4 to the 4th. It rises geometrically, right, with the number of dimensions. Even if we have only 2 states we can be in for a new dimension, we double the model size. And that leads to a lot of states in the model. It leads to longer run time. And meanwhile, doing so within an agent-based model where we can represent multiple state charts, it's additive. We might add 2 additional possible states by representing an extra bit of information, 1 or 0, for whether someone is diagnosed or not, for example. That difference, multiplicative versus additive, is a big difference, and it can get large, very large, as we add in new states, as we add in changes of someone's age, among age groups, someone's sexual risk behavior level, someone's smoking status, someone's status with respect to STI1, someone's status with respect to STI2, etc. That combination can become fearsome. But I hope you'll recognize that the bigger issue here is often that of model transparency. It's really this issue of these 2 things. The transparency of the model is reduced. It's more obscure because we have so many different combinations to consider, particularly as we add a third, fourth dimension. And in terms of modifying it, a modification, if we wish to add an asymptomatic state, for example, for COVID, we would have to add say, an infective state that's symptomatic, an infective state that's asymptomatic, for each and every one of these here. We'd be needing to modify the model at many places. And in general, if we have to add another dimension of heterogeneity in, we have to do so across the breadth of the model. It's promiscuous. It gets us into touching it at many, many places and the risk of error at many, many places. By contrast, adding things in within a context of an individual level model means adding in a new state chart, for example. It's a comparatively localized, comparatively sort of surgical type of change that doesn't require mucking around with all the other pieces within the model. In general, there might be some ways, maybe adding in the new state chart, you need to add some statistics to be accumulated. You might need to add some ways in which interventions might affect that state chart. Maybe you have some interaction of that state chart with one other state chart in terms of changing the risk profile. So maybe here, if you add in a state chart for care seeking, you need to characterize a linkage between someone's infection status and whether or not they seek care. Or maybe you have a model of their smoking status and their heart disease status. And when you add in heart disease as a new state chart, you need to make sure smoking affects the risk of developing heart disease. But it's a comparatively small, localized type of interaction that you need to characterize, rather than the kind of brutal, uniformly modifications across the entirety of the model. So when it comes to state, when it comes to aspects of state here, we have many benefits of an individual-based model. The ability to characterize memory-full transitions, the ability to simultaneously track individuals along multiple dimensions, and to do so in a way that helps boost model transparency, and the ability to nimbly add and remove heterogeneity. But further, models have the ability to accumulate history information, my number of pack years I've smoked, the number of years I've spent obese, the number of times I've attempted to quit, the number of times I've been infected by COVID. And finally, we have these scaling relationships that mean that the model size for a representation that's aggregate, that's cross-sectional, rises geometrically, multiplicatively with each new dimension, but only additively in the context of an individual-based model. So those are some characteristics of representing state and state heterogeneity of multiple evolving processes within agent-based models. Within our next lecture on Wednesday, we're going to be talking about ways that different agent-based modeling platforms and approaches characterize the key task of evolving model state. Here, I pointed to state charts as something that simultaneously gives us, at one glance, a characterization for a given concern of the states that someone can be in, the types of actions that can change that state, those states, and the rules that govern those actions. But this is just one way of representing characteristics of a person. And there will be needs for additional ways, particularly for things like relational information, for things like continuous information on the part of a person. And we'll see here that while state charts afford us a certain economy of representation, there's a whole wild west of different ways of representing rules for updating agents. And we'll be taking a look at that crazy quilt next time, and seeing some more structured declarative ways of doing that, and some ways that are far less structured, but very commonplace with code. And we'll see different types of languages used for this. So that's on Wednesday. And I look forward to joining you to deliver that lecture next time. Okay, so those are all for today. So we're going to. Okay, so Matthias asked a very good question. So suppose you have a state chart, and the state chart conceptually reflects, say, increasing levels of risk. So in this case, mortality without heart disease and mortality with heart disease. And you have some progression along here, maybe given by rate, from a healthy heart to developing heart disease. In the healthy heart state, you have some lower risk of developing of mortality, and in the heart disease state, you have some higher risk per year of developing mortality. Yeah. A higher probability per year. And Matthews was making the salient observation, or insightful observation, that in this situation where in any logic you come in here, you draw for a healthy heart, which one of these will occur first. If it turns out this one will occur first, you'll proceed down here rather than going this way. And coming into this state, now there's a possibility that this will be drawn, like the timing of this coming in here could be drawn so that by developing heart disease, you will actually leave this side from here. It could be that, by chance, it drew this to be 10 years, this to be 12 years. You ended up leaving with this transition, you develop heart disease, and now it draws this, and it so happens that it draws 5 years. And you would have developed heart disease within 12 years, had you gone out via this, you would, had this not occurred, you would have developed it in 12 years. Here, by going here, now you have 3 extra years of lease on life, right? Because you already accrued 10 years waiting here. Now you come across, and now you draw 5 years, and you will be able to, you'll die 15 years in instead of 12 years in. That's the idea. And that is a risk. Agreed. Now, Nadius was asking, could you somehow count this time spent here accruing? This is going to appear, in 2 years, I would have gone this way. And somehow when you transition to year, say, well, I'll make this one capped, as it were, by occurring no more time than would have occurred this way. So you sort of preserve this risk, as it were, or you limit it. Now, it's actually an idea we've talked about considerably in some other contexts, including this categorical APM platform we're developing. It is tempting, but it's notable that it occurs in, it's a concern not in every situation that looks like this. Like, there may be some transitions here where you're actually going to a lower risk state, right? and where it's perfectly reasonable that this gives you an extra lease on life. So it's not every transition that you would want to cap this to be no larger. If you want to start to think about it more critically, could it be that if this is a higher rate of leaving, a higher hazard rate than this, you don't want it to draw a number that is less, the timing of it should be no later than you would have gone with this lower hazard rate. You might be able to do so, but delineating those cases, like getting the user to proactively think about that and say, like, this is a case I want to enforce that constraint, could be challenging. I will say that it would be possible. I mean, agent-based modeling being what it is, and AnyLogic being an agent-based modeling platform, this could be implemented manually, right? Like, you could draw this from a distribution explicitly as a timeout, for a timeout. You could draw it from that distribution. You could count the number of years you've accrued towards it, how long you've been in this state. When you transition, you draw this from a distribution, counting those years as accruing towards this, right? You could do that. And you could actually, for this particular case, have it capture it in a sensible way, that developing a worse situation doesn't give you a new lease on life. It doesn't extend your life. That could be done. It is sort of troubling, statistically, that you might end up with receiving a longer time here. But I will say, like, I think there might be a better treatment that could be done statistically by talking with an appropriate statistician, because really what you have here is competing risks, and you have censoring going on. Like, the fact that we went this way censored this event. And there's probably some in the literature, there's probably some good treatment how to handle censored events in transition-based models, or in the context of transitions, that might give a better way, a more principled way to handle this. But yes, it can happen that, perversely, you transition to a worse situation, which has a lower chance on average for the time to go this way. You go here on average sooner, but it so happens by the luck of the draw, this is drawn such that you have extended life by going this way rather than here. Yeah, I think I'll talk to my colleague Jusha and Leo, and I'll see if she can help me sort of formulate a better solution to that. Yeah, no, it does happen. What's that? Yes. And two models. Okay. Two AnyLogic models. Yeah. Yeah. Uh-huh. Right. Right. Yes. Yes. Right. 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 Yeah. Yeah, because sometimes when you change state, it's that changing state gives you a chance at getting a longer time, and you can't get time sometimes.
And then the weird part was the people that lived the longer were not the ones that remained in house weight all the time.
Right.
It was the people that swapped.
Right. People moving back and forth a lot.
So like,
you end up sort of artificially getting this artifactual thing that moving into a new state allows you to, because it lets you roll the dice, you can end up getting a higher, it gives you a chance of having your time extended, but it's asymmetric in the sense that you don't have an equal chance of having your time reduced by the same amount. In some cases, it's, I mean, because you've already spent the time, you can't, in that case, go in less than 10 years, to there. So that's okay. You've got me interested further in this. I think there's probably a good principled way to deal with this biostatistically, and I got to speak with Jushin Liu, and she'll probably put me on the right path about this thing. Cool. Okay, so folks, I think you're aware that Mondays I haven't been able to promise office hours every Monday. We have office hours on Wednesday and Friday. Today, I apologize. I wanted to offer what I could office hours, but because there's this defense that I need to sort something out